Welcome back to the next video, everybody. Sorry I had to take the day off yesterday. I am busy preparing for some talks. So today we're going to be looking at the classical versus the modern theories for GL2. We're going to start trying to see how we might attach some automorphic cuspidal representations to our new forms. So first, a little motivation with GL1. Recall from a previous video that Dirichlet characters correspond to special automorphic representations of GL1. They were the grossing characters of finite order. We talked about this. Okay, we're going to look now at the analogous result for GL2. So here's the theorem, theorem 4. There's a bijection between the set of new forms F with Fourier coefficients A sub n and S sub k of gamma 0 and psi, and the set of irreducible automorphic cuspidal representations pi equals tensor over p pi sub p of G of A sub q, where A sub q are the adels for q, such that the central character of pi is chi sub psi. Chi sub psi was defined last video. Pi sub p is unramified for all primes not dividing n. And pi sub infinity, the Archimedean local component, has lowest weight k that was also defined either last video or 2 videos ago, these lowest weight representations. Moreover, if we take n and factorize it into primes p sub I with exponents alpha sub I, then pi sub p sub I, the p sub I local component of pi, actually has conductor given by this exponent, as it should. If p doesn't divide n, then pi p is pi induced by the character mu1, mu2, where mu1 and mu2 are unramified characters of qp star, such that p to the k minus 1 over 2 times mu sub 1 of p plus mu sub 2 of p is actually a sub p, where a sub p is the pth Fourier coefficient of f. So that's interesting. And so what do we want out of this? Corollary, let's look at new forms representation theoretically. A new form f in S1 gamma 0 n psi with eigenvalues a sub p is the same thing as an automorphic cuspidal representation, tensor over p, pi sub p of weight 1, such that a sub p is mu sub 1 of p plus mu sub 2 of p for all p not dividing n. For a proof of this, you can see CSS page 171 for a sketch. Its references give much more details, though. Gelbar's book, chapter 5, is an excellent source as well, his book on automorphic forms. Okay. What is mu sub 1 and mu sub 2 here? What are those? Mu sub 1 and mu sub 2 are the two unramified characters of qp star inducing the unramified representation pi sub p equals pi sub p of mu1, mu2 of GL2 of q sub p, like we just talked about 2 slides ago. Okay, well, the relation, so we have this relation a sub p equals mu sub 1 of p plus mu sub 2 of p, right? So we have this. What we do is we rewrite that basically. We rewrite that as a sub p equals the trace of t sub pi sub p, where t sub pi sub p is the 2x2 matrix in GL2 of C with diagonal entries mu sub 1 of p, mu sub 2 of p, and 0 entries elsewhere. And this allows me to finally define something for you that I've been talking about for several videos, which is the Langlands class of the local component pi sub p. It's merely this matrix, right? And so a sub p is just the trace of this matrix. That's how we think about this, because this matrix is very important in the theory. Okay, before going on, we should recall theorem 3 because it's been several videos and I'm a nice guy. Recall that this entire time we've been assuming the following: in the case k equals q, in the case rho factors through g sub q, and in the case rho is odd. So rho of complex conjugation is -1. Theorem 3, I've already stated this in a previous video. Let k be a number field. To each irreducible solvable representation rho from the Weil group of k to GL2 of C, which I still haven't defined Weil groups yet, there is an automorphic cuspidal representation pi of rho equals tensor over v pi sub v, where v are the various places of k, of GL2 of a sub k, the adels of k, such that the central character, which I've now defined, of pi of rho equals det rho, and trace of the local Langlands class at v equals trace of rho of Frobenius at v for almost every prime v of k. This is a theorem we've been assuming throughout all of this. Now, if we continue to assume this theorem, just in the case k is q, rho factors through g sub q, and rho is odd, we are now in a position to prove that automorphic Langlands tunnel implies classical Langlands tunnel, which is one of the loopholes that we have not yet closed for the chapter. So let me show you how to do that. It's very easy now. Suppose rho from GQ to GL2 of C is a continuous, irreducible, odd, solvable representation, adjective soup. By automorphic Langlands tunnel, there's an automorphic cuspidal weight 1 representation, pi of rho equals tensor over p pi sub p of GL2 of a sub q, as usual, with central character det rho, such that for almost all primes p, pi sub p is pi of mu1, mu2, is unramified, and trace of rho of Frobenius at p is trace of the local Langlands class at p is mu sub 1 of p plus mu sub 2 of p. We know all of this. Okay, but by the above corollary, there's a new form F with Fourier coefficients a sub n and S1 gamma 0 of n psi for some n and psi, such that a sub p is trace of rho of Frobenius at p for almost all primes p. Okay, but this is just the classical Langland's tunnel theorem, right? So we're done. And so let's do a reality check. What do we have left to do? Well, we haven't proven Langland's tunnel yet. We haven't proven automorphic Langland's tunnel. Okay. Given automorphic Langland's tunnel, though, it now suffices to prove theorem 3 in the case K is Q, rho factors through G sub Q and rho is odd. So we have to do that. We have to prove theorem 3 in a special case. You also might have noticed, though, if you're being astute, theorem 3 doesn't give us the weight 1 condition we seek on pi of rho from automorphic Langland's tunnel, if you go back and look at automorphic Langland's tunnel. But we will see very soon, it will be easy to see, in fact, that pi sub infinity, the Archimedean local component of pi, is just pi of the characters 1 and the sign character, i.e. that pi of rho is weight 1. This will all follow. In other words, the weight 1 condition that we seek will all fall out of our already known information easily. We'll see this later. So that is not actually really, it's a tiny loophole in the sense that we haven't seen how it falls out, but it's not really a loophole in the sense that there's actually nothing really to address there. Okay, so we have to prove theorem 3 in a special case. We have to, I guess, make sure we have the weight 1 condition of automorphic Langland's tunnel. And then once we've done that, all we'll have to do is actually give a sketch of the proof of automorphic Langland's tunnel, and the chapter will be done. The Langland's tunnel portion of the proof of Fermat's last theorem will have been dealt with. I'd like to interject here a remark about strong multiplicity 1 to conclude this video. Strong multiplicity 1 is a theorem for GL2, and it tells me that two automorphic cuspidal representations pi and pi prime are equivalent if they are equivalent locally almost everywhere. What does that mean? That means the local component pi sub p is isomorphic to the local component pi prime sub p for almost all primes p. For example, this theorem, it turns out, is used among other places in the proof of the fivefold theorem from chapter 1, way back in my playlist, and also in the proof of theorem 4 above, the one from this video. Another interesting application of strong multiplicity 1 is that it implies that the pi of rho from theorem 4 is unique if it exists at all. It also implies that in the classical Langland's tunnel statement, the new form G is uniquely determined by the given trace condition on it that we gave. And so if you were paying attention again carefully, you might have thought that the theory of new forms is actually just weaker than the theory of certain automorphic cuspidal representations based on the remarks that have made in the information I've given you this video. But strong multiplicity 1, in fact, tells you that no, it's not weaker, it's equivalent. So again, the classical theory of new forms is equivalent to the theory of certain automorphic cuspidal representations, not merely weaker. If you would like a good reference that I really enjoyed, for the proof of strong multiplicity 1, you can see Fang-Whitaker models and multiplicity 1. All right, so next video, we'll begin trying to tackle the couple of loopholes left that we still have. So I'll see you then, and thanks for watching.